Hello everyone, welcome to today's video where we're going to redesign this drill battery BMS. I went to put it together this week and make a video about it, and I'm not happy with it. In fact, I hate it. It's not that it's a terrible design, but it is just not up to what I think it should be. I cut a few corners where I shouldn't, and we can make it a lot better. And so, since this is my channel, we are going to make it a lot better. So, I'm going to show you what I'm going to do to improve this design, and it is going to be amazing when I get done with it. So let's get started with today's video. So one of the first things we need to do is update the schematic. Now, there aren't going to be very many schematic updates. The main part is going to be the layout, but we do need to update a few things on the schematic. So we need to update our input connectors. So if I take and rearrange these and do that, our input connectors are currently these JST headers, and they're perfectly fine for the design like this, but I'm going to take the components and put them on the bottom. That'll be part in the layout. And so I'm going to change them, instead of right angle, I'm going to change them to vertical headers. And just to note, when you do something like this and it's going to be on the bottom side of the board, you need to go ahead and have the mentality that you're going to have to glue them in place. I'm going to use silicone to make sure that they stay locked in place. I'm going to put a little silicone or maybe some hot glue on them. But if you're doing that with a board that's upside down and the connector's coming out of it vertically straight down, there's going to be a lot of force pulling down on that whenever the pack is in transition or transport or being used and being vibrated. So just with that mentality. But I'm going to change these connectors out to ones that are vertical. Vertical instead of horizontal. So the B4B pH, what we originally had in here before we changed it in the last video, and then the B6B pH by JST. So I'm just going to change these out. Now you can go through the whole library tool and all of that and change out the connector and all those kind of things. I'm lazy. Here's the way I do it. I'm just going to delete J4. I'm going to put this in J4's place, and then I'm going to rename this J4. So, and you want to pay attention to your pinout organization too. So if I go back 1 through 6 and then go forward, it is 1 through 6. So you want to make sure you pay attention to your pinout, because J3 has been reversed. It is 4 through 1, and so we're going to have to change that. Now, I know that I'm going to be putting this on the bottom, so the pinout of this is going to be reversed. So I'm going to go ahead and flip this over so that way the pinout will be correct when I put it on the bottom of the PCB. Same thing with J3. I'm going to delete J3, and then I'm going to put this in here in this orientation, rename it to J3, and it should be correct when I go to put it on the bottom of the PCB. So just be thinking through those kind of things whenever you go to make changes like this. Also, the output for system present. I'm no longer going to put a switch on the design because the quiescent current of the BMS chipset is not that much. It's like 18 microamps. So it's not very much. So instead of putting a switch on it, what I'm going to do is I'm going to put 2 pads with a jumper in the middle in case I want to put a switch on it, or in case I need to put a switch on it in the future. Also, I'm going to put a pad for the thermistor. So let's see what that's going to look like right here. So we're going to eliminate J2. I'm going to eliminate these 2 nets here. I'm going to keep thermistor 2. So for system present, I'm going to take, and I'm going to put a solder pad here, a 2x4 solder pad. Now, I've already put that in my library here, a 2x4 solder pad. So I'm going to put that here, just like that. And then I'm going to take a 0 ohm resistor, or just a 100 ohm resistor. That will be fine. I'm going to take a 100 ohm resistor. There is my 0 ohm resistor. So I'm going to put a 0 ohm resistor here, and then another pad here. And so what that's going to do is it's just merely going to jumper, the 0 ohm resistor is merely going to jumper system present to pack plus, which is the way it should be. However, if I did need to put a switch into this design, I'll have pads on either side of this resistor. I can just depopulate this resistor and then put a switch between these two pads and be able to control it externally. So when you're designing, just try to think ahead about these kind of things, just to try and, future-proof it in case you need to. And then for thermistor number 2, I'm going to delete it. And then for thermistor number 2 on the output, I should not have deleted it, excuse me. For thermistor number 2 on the output, I'm going to put another pad, 2x4 pad here. And then that will be an output pad for your thermistor. So I am going to label all of this. So that's already labeled pack plus, pack minus, and then this will be labeled thermistor. And that'll be labeled thermistor just like that. And then that'll be your thermistor output here. So just a few updates to the schematic, not many. So we changed our 2 input connectors. We got rid of our output connector. Now we have a main power pad positive, a main power pad negative. We have our main pad for our thermistor, which is going to solder to our to the blade connectors that are on the output of the pack. And then we have a system present optional switch in case we need it in the future. However, I don't think we'll need it because, again, the pack does not draw that much quiescent current. I think it'll be fine because it will be regularly used. Now, if this was going to be set on a shelf for months at a time, you definitely want to be able to turn off the BMS. But this pack is going to be regularly used, I mean, almost daily here in the lab, so I have no worries about it being connected to system present all of the time. So that's all of these schematic updates that we are going to do right now. We just need to annotate, and I'm going to annotate schematics quietly. That is a good feature. I'm not going to re-annotate the whole entire schematics. I just want to re-annotate it quietly, which selects the components that do not have designators and then just goes ahead and assigns them designators. However, I am going to name these manually. So I'm going to call these SYSP for system present 1, and then I'm going to call this one system present 2. So I'm going to go ahead and name these manually and then adjust how they look because looks is half the battle. But if I annotate schematics quietly, one designator, that designator is R26 here. The 0 ohm resistor R26 is the designator there. So let's get into our PCB layout. Okay, so I've taken and went ahead and renamed everything to revision 2. And so we're going to go design, update PCB document, automatically create component links, don't add the room, execute changes, close. So this is what our current PCB layout is. And so we're going to be starting pretty much completely over. So let's do that right now. Let's start completely over. So what I'm going to do is I'm going to select all of my components, and we're just going to move them out of the way. All of our components. And then I'm going to go select everything, Shift S to isolate the top layer, delete it all. Oh, excuse me, hold on. I need this guy because I'm going to keep that text and delete it all. Bottom layer, and we're just going to delete it all. Just delete everything. We're going to fix it all. So what is it? What layer is that gone? Oh, that is on the top silkscreen layer. So now we just have our outline layer and then our top overlay layer. So let's start back with putting our outputs and inputs back. So I'm going to change my grid 1 millimeter. Now, the battery plus input and the battery minus input are going to switch places because we are doing the components on the bottom side, which means the inputs and outputs are different. Now, I can weld the cell stack any way I want to, so I'm just going to weld the cell stack in reverse of the way I was going to do it, and now your minus is here and your plus is here. So I'm going to switch to these two. I'm going to put my B minus here. I'm going to put my B plus here, and I'm going to stick my battery ground here. So I need to take and rotate this. So I'm going to say move, and then I'm going to say rotate selection, and I want to rotate at 80 degrees, excuse me, from what it is now. And that did not work. rotate selection 90 degrees, not 180, 90 degrees. And there we go. So there's that. I want to get it roughly in the center of this. And then the same thing for my battery plus, which is now moved. Move, rotate selection 90 degrees to the center, and then we're going to move it in place as well, just like that. Now, are they even? 14 and 49, and then this should be 14 and 13. Let's just measure that just to make sure. From this corner to this corner, we're looking at 14.75 and 6, and then from this corner to this corner, we're looking at 13.75 and 6. So, which one do I want to move? Let's see. Which one looks better? Let's move this one up 1 millimeter, and then that should be Control M is your measure, 14.75 and 6. So there we go. Perfect. So there are our input pads, and then we're going to do our output pads now. So our pack plus will be down here, and I'm putting it down a little further than it was in the other design because when I went to look at the mechanicals inside of the pack itself, inside of the drill pack itself, I did not like where the wire is going to have to bend around and solder to the output connector. So I'm going to move them slightly. So I'm going to put it in line with this and 5 millimeters away from that, so that is even. And then pack minus, pack plus, battery minus, and battery plus. So there we go. There are our input and output pads. Now I'm using, instead of using through holes to solder my wires, I like to use pads. The main reason is surface area. The more surface area I have, the more current I am comfortable with carrying. So we're going to be putting 12 gauge wire. I'll back them up 2 spaces. We're going to be putting 12 gauge wire into this design. That can handle the 23 amps just fine in the 1.5 inches or 2 inches of bend that the 12 gauge wire is in. So I want to make sure I have as much surface area as I can with that wire contacting the copper. And the best way to do that is with a solder pad instead of a through hole. Right, so let's move on to our FETs. So these are our output FETs. Spin them around, and there we go. There are output FETs. Now, I am going to adjust the board outline just slightly because when I was doing the mechanical, it turns out the board outline can be adjusted from what it is. So I'm going to move this over 1 millimeter and this over 1 millimeter because it was encroaching on the board, on the latches for the board design. I'm going to move that over slightly, and then I'm going to move this up 3 millimeters. So 1, 2, 3, because it did not need, excuse me, to be as big as it is. So bring that over, bring that up, and then bring that over, and then bring that over, and then bring, what is it? Oh, it's snapping to the middle of that. So let's move this up, have that go back to there. Make sure you watch out for your grid when you are doing these kind of things, because sometimes it'll snap to a different point that you don't intend to. So make sure you do that. So let me get this other side finished, and then we'll keep going. And then these holes need to be adjusted as well. They can go up by a few millimeters as well. So I'm going to take and get as much room as I can. You want as much room as you can. So I'm going to take these up. They can go up by 3 millimeters as well. All right, now that our board outline is fixed, we're going to go Shift S, select, and then board shape, design from selected objects, and then there we go. That is our new board outline. We have a little bit more room for copper, which is good. So Shift S, and then we're going to start back here. So we're going to start laying out our stuff. So this is backwards. I made that mistake. This is backwards. It should be this way, and then I'm going to take and move my capacitors here, just like this. So that's our input and output for that. Then I'm going to grab our current sense resistor, which is here. We're going to put our current sense resistor right in the middle here, just so it looks even. It doesn't really matter, but we're going to put it in the middle so it looks even. And then we're going to take and place our fuse. Our fuse is going to go, again, somewhere in the middle so it looks even. And then we're going to do the rest of our layout. So the first thing I'm going to do is change our layers. So I'm going to go to our layer stack manager, and we're going to make this a 4-layer board because it's easier to route everything. I'm going to make the top as much copper as possible, which means I need a 4-layer board to carry. Will mainly be a ground plane is what I need a 4-layer board for. So we're going to insert layer below, it doesn't matter, and we're going to do a signal layer below. And so we're going to call this, instead of top layer, layer 1, then layer 2, then layer 3, then layer 4. So the reason I chose signal is because I plan to run I plan to run traces on either plane, but really I'm going to dedicate one to a ground plane, but they're both not going to be plane classes. So just so that's clear. And you can get away, this is not a high-speed signal design or anything, or it hasn't got any kind of high-voltage signals or nothing. So you can get away with that pretty well. So that's our top layer. This is everything that's going to be on our top layer. So let's start in on our bottom layer. So the first thing I'm going to do on my bottom layer is change the these two connectors to our bottom layer and then move them. So I want to do my inputs and my outputs. Now I am going to spread them out just a little bit, just so they have plenty of room. I'm going to align the edge with the edge of this just because it's handy. So I'm going to align the edge to this, edge close to this as possible, just so they look even. Now, if you'll notice, this connector already has through holes through it. I do that sometimes in order to have a dual footprint. However, I do not want that. So I'm going to go to my PCB library, and I'm going to go to that footprint, which is this one here. This is go back to our schematic. This is the B6B that we're using, and I do not want that in my design. So I'm just going to take and simply delete all these out, because I don't want it to impede the copper on the top layer. So I'm going to simply delete all those out, save, and then I'm going to update my PCB with this. And sometimes it does not work. I do not know why, but sometimes it does not work. So I'm just going to simply delete this off, and then I'll go back here, update my design, and then it'll put it back in here for me. And then it will be correct. So there we go. Flip it over to the bottom layer, and there we go. So again, align it kind of where we want it to be, just like that, and then kind of where we want it to be, just like that. And there we go. That is our connectors for the bottom layer. That looks good. Maybe scoot them back slightly a little bit more. Let's go ahead and get them back as far as possible, because we don't want it to impede on the cell stack. So we're going to get it back as far as possible. Okay, there's our thermistor connector, and then there's our cell connector. Now to the other outputs. So the last outputs to route would be these pads, and that will be the system present pads and then the thermistor pads. So what I want to do is I want to put a line in the middle of this. I want to put a line in the middle of this PCB. So what I'm going to do is I'm going to put a line here to here, and then I'm going to take and put a line right here, and I'm going to take this line and I'm going to snap it to the center of this. And then I want my end point to be, I don't know, or my length. I want my length to be, I don't know, 40 millimeters. No, that's not enough. Let's say 100. And so that is the center point of my PCB. That is between here and here. So I want to I want to kind of center things. Things that got to be completely centered. That's fine. But I want to kind of center things. So I'm going to spread that out a little bit, spread that out a little bit. Text. We're going to do top overlay. This will be Pack Plus. Let's increase the size of that a little bit. Let's go 1.5, 1. Let's go 1, and then 0.2. This will be Pack Plus. Hold down Control so you can line it up. Control C, Control V, and then this will be System Present, and then this will be thermistor. Just like that. So those are our output connections right there. So we have power ground, Pack Plus, and then we have our Pack Plus here for our jumper to system present. And you know what? That is stupid. Hold on. Let me even make mistakes when recording, but I'm not going to edit it out because I'm too lazy. So Pack Plus really should be here because that's the side that Pack Plus is on, and then thermistor will be here. Because that's the side thermistor is on. So there we go. And that is all of our inputs and outputs routed. So let's get to doing the rest of everything. Now, I will admit, this is not as smooth as I would like it to be, but I'm still not very good at recording and doing layouts. I kind of stumble over myself, and then I don't really have a plan. I'm just kind of winging it to do this. I haven't done a pre-layout before, and then I'm showing you what I did. I am just winging this. So, yeah, that is what's happening. So, I'm going to take these resistors here, and I'm going to put them on the bottom layer, just like that, and then I'm going to take and flip them over. And I'm hoping this is going to work, but I'm going to take and flip them over, and then that will be... Those should all be correct and lined up. Yes, that is right. They are all correct and lined up. So when I bring my main chipset over, they will be correct and lined up. But I want to take section by section. So because this is a reverse of the top layer, I'm going to take it section by section, flip those over, and then take them and put them in their place. Because you can't really flip the whole thing over. You can't flip the whole thing over. You rotate everything. But if you were to rotate everything like it was on the top, then your inputs and outputs would be reversed. So you have to take it section by section. So I'm going to take layer 4, and then I'm going to take and go over and then flip that. Now, one thing I am going to have to correct, all of my designators are wrong. They're all reversed. So that is something I will have to correct later. But make sure all of those, all those looked lined up correctly. I think I need to scoot them down. Yeah. All those looked lined up correctly. Also, I'm still on a 1mm grid. I'm just trying to get things in general place. I'll change my grid and align everything properly here in a minute. But I'm just trying to flip everything over and get everything in its general place. Let's take this section, layer 4, and then we're going to take and flip it over like this here, and then these 3, wrong button, and then these 3 need to flip like this. Yes, just like that, okay. And then we need to go back over here to our, let's put those back. We need to go back over here to our current sensing section, which is this section. Let's move it next. And then we need to flip that and then rotate it. And then that should be 13 and 12. So that should be correct there. So we're going to go ahead, move that there, put that there. And then the rest of this will just route as needed. So let's take everything, put it on the layer, and then just rotate it. Just like that. And a lot of this will translate back to the bottom quite easily. So we've just got to remember where everything went. So let me do a split screen here so we can see both. So D2, R17, and R22. Let me make this a little bigger so we all can see. And then there we go. So D2, yeah, that's what I thought. That's all part of the FET section. So we'll set that there. Layer 4, and then R23 and R24, I think, are still part. Yeah, they're still part of the FET section. So we'll take and put those over here. And then where are the FET resistors, and what is that? Oh, it must have just been it was just a, there's a weird glitch right here. Does everyone see that? I don't know what this is. I'm just going to ignore it. It's fine. I'm just going to ignore it. There's nothing there. There's nothing there at all. I just it's a glitch. I don't know what that is. And then we've got the rest of these resistors over here. So, let's get to routing all this like we would normally. So I'm going to take and scoot this section as close as I can get it over to the cell connector, and then I want to change my grid to 500, and we're going to get all of these put together. I'm going to do this a little nicer than I did last time. I don't like how it turned out last time. So we're going to do that. That will be our FET section, and then our section here for our capacitors. So I remembered why these were spread so far apart in the first design, and that was because to make it look even. I spread it apart to make it look even. So that's what we're going to do here. Is I'm going to make it look even again. So I've done it to where when these are centered here, the line that goes down will barely pass the capacitor, and then it'll be even when it goes in. So let's route these just like that. And then this goes here just like that. Spread it apart a little bit. And then this goes here just like in the middle. Just like this. And then this goes. There she is. And then this goes here just like this. So now we should be able to take VC5, route it directly to the chipset, and now this connects here, and then this routes directly to the chipset, and this connects here, and this connects here, just like that. Same thing with VC3. It will route directly to the chipset. Here. This will route directly to the chipset. And then here. And here. And this will route directly as the others. If I can get a bend out of it. And then correct that. And then that will route here. And then this will route with a slight angle here. And just like that, still looking even, of course, because we want it to look even. It's all centered on the center line, but we want it to look even. So we have that. And then VC0 will route the same exact way. If I can get it to, again, put a little bit of a bend in it. There we go. And then we'll move that one down slightly as well. And then there we go. There is all of our cells routed. Oh, not to forget the ground as well. So we need to do that. Delete the little tail off. Back minus, and then we'll copy that. And then paste that here. And just like that, there are all of our cell inputs routed. So now let's turn our attention to the main input. So R1, which is here, is a not fitted, but that connects to the main power rail. I always do that in case the individual sense wire does not work. Normally it does, but sometimes it does not. Oh, I forgot to put this here for the cell routing. There we go. But sometimes it does work, sometimes it does not. I'm confident that it will, but that's just here just in case it does not work. So I'm going to do this, and then I'm simply just going to put a via here because I know that my plane will be running through here. And so let's turn our attention to the input of the chipset. So this is our AVDD capacitor. This is our reserve capacitor. So I'm going to change back to a normal width trace, and we're just going to do everything like we normally would. So here is our voltage input, our voltage capacitor, and then again our ground point. So I want to try to minimize as many vias as I can because again this whole top is going to be a copper port to carry the most current. So I want to try to limit as many vias as I can. I'm going to try to keep it under 20. That is my goal, to keep it under 20 vias for connecting to the ground plane. But we'll see how that goes. I don't know if it'll work or not. So that is our main power input, of course, run, and then we're going to go our R2, goes to R1 over here and everything else. So that is that section routed. So let's go turn our attention here to the rest of the chip down here. Pin number 9 is a bat minus pin, and so we're just going to take and put a via under the chip. Now that is fine. Pin number 9 is VSS. Putting a via underneath a chip is fine, as long as it's a leaded chip. And the reason I say that is this. So you see, it sits on leads. It's not technically sitting flat against the circuit board, or it doesn't rely on sitting flat against the circuit board. So it's fine to use vias underneath it. But things like capacitors and stuff, like these capacitors that rely on sitting flat on the circuit board to make their good connections, the package itself sits against the circuit board. You don't want to run traces or do vias underneath those because there's no room underneath to run your to run your tracks. It'll lift the component up, just in case you wanted to know that. But pin number 10 is your SRP, pin number 11 is your SRN, and then pin number 12 is your discharge. So here is our current sense resistor here. So we're going to do our routing of this. Now all of this is backwards, so we're going to have to reverse this. So we're going to rotate this. No, we're going to leave this. Yes, we're going to leave that the same. Change that. We're going to change this around, move our silk screen, change this around, and move our silk screen just like that. So now it's going to route properly, and I'm going to try to sneak it as close as I can over here. Try to keep everything as tight as possible. R12, and then R13. Now these traces do not have to be even. A lot of people will get very angry when they see that designers do not do that, but they do not have to be even. It is fine. You will not break everything by them not being even. And then, is this really where I want my current sense resistor? Let's check that. Is that really where I want my current sense resistor? I think that's fine. I think that's where I want my current sense resistor. By the way, if you're wondering how I'm manipulating the board and the space so well, It is this 3D Connection Space Mouse. I'm not sponsored by 3D Connection, but it's great. I've used it for, I don't know, I've had this one. What's the date on it? Let's see. It doesn't have a date on it. I've used it for at least 5 years. It's their wireless model, 4 or 5 years, and it's great. I love it. Just want you to know that I love it. It's great. So that's how I'm able to manipulate all of this space, especially my paper space and then my 3D space, and then I'm able to manipulate the board the way I do is because of this space mouse. So great investment. I love it. I could not imagine designing without it. So if anybody out there listening from 3D Connection, you know, if you wanted to sponsor me, send me some free stuff. I'd love that. Send me a new space mouse. The battery in this one's going dead. And I'm too lazy to pull it apart and change it. Plus I'm a little worried that if I pull it apart and do something, I might hurt something. So, yeah, if anybody from 3D Connection is listening to today's video, just 331 Shelley Brook Drive, Pilot Mountain, North Carolina is where Protechnologies is located, which is who my employer is and who is sponsoring this video. So I'm using, of course, their facilities and then their Altium license and everything to do these things. If you follow me for any length of time, you know that I'm a battery designer. I'm a BMS designer. And I work for Protechnologies here in beautiful Pilot Mountain, North Carolina. And so I'm just sharing what I've learned over the years with you. And if you would like a custom battery pack with a custom BMS designed by yours truly, a great engineering team that we have here. We do plastics designs. We do it from all the way from the ground up. We can take you from concept, and then we build products here. Behind this wall is where the plant is, and then we build it and we ship it out the door. So all we need is a design from you, and then we can send it to you. So Protechnologies, sales at protechnologies.com. Tell them I sent you, please, because I need some validity to what I'm doing here. I'm sitting all by myself on a Friday evening, all alone here. All I have is the creaks of the building, and I'm pretty sure there's some ghosts in here, too. I think there were some things that went on back in the day that I don't know about. I'm being haunted or something. So, please like, share, and subscribe, and contact sales at Protechnologies because it's awful lonely here. Hopefully, I'll get to go home one day. Anyway, so let's get back to routing everything else. So R15 is our discharge line. I'm not going to worry about that right now. 12 and 13 are charge and discharge. I'm not going to worry about that right now. Let's go to 23 and 24, which are both grounded. So let's do this to a via, and then we'll just do this. I don't like to do a copper pour or connect these pads together because sometimes during the manufacturing process things can mess up. I just don't like doing it that way. Pin 22 is our system present. Okay, so now we're getting into the works. You know what? I'm going to take and I'm going to move this down here. I'm going to take and I'm going to move this connection down to here. And then I'm just going to take and go out, over, back around, just like that. And so I can have enough room out here to do all the rest of this. So I'm hoping most of this is still the way it needs to be, so I haven't got to do a whole lot of extra routing, but we'll see here. So R11, let's scoot him. Let me select all this again. Hold on, shift, I don't want to select this. And let me, I think it was probably about like that. Let's see how that works right there. So R11, going to my system present, and then R7, and then thermistor, and then R9. That's another battery minus. Where does pin 16 go? 16. Oh, that's just your cell balance input. That's your cell balance enable pin. Okay. And then R18, and then R16. Okay. So R8, so R7 is the thermistor pin. R7 is your pull-up for your thermistor. And then R9 here connects to your. So we can tighten this layout up again. Again, I'm just winging it. I have no plan. Again, I'm just kind of winging it. I have no plan. And so let's see if we can tighten this up just a little bit. R9. Is that enough room? No, I'm going to have to scoot that back a little bit. So let's do this and try to tighten this up as best we can, because I do want it to look nice, and I want it to look like there was some care given of how this layout is turning out. And then, nope, that is not going to work. I do not like that. So let's move that back up even with that. And then we'll do that. We'll do that. And then we'll do that, just like that. Okay, I'm happy with that. And we can even move this back up. I think we're just right back to where we started, but it's okay. Move that right back up. And then we can set net 18. We can take R18, move it into place, and do it a little better. And then bat minus, of course, here. Okay. And then that goes to power ground, which is out here. And then this goes to our FETs. Okay, so that's all of that routed. Now let's get to our FETs. Now to our FETs. So the first thing I'm going to do is do our FET input resistors. I'm not sure which one they are, so I'm just going to do this. Right-click, part actions. Right-click, part actions. Sometimes it doesn't work. Right-click, part actions. Select PCB components, and then reposition selected components. And we're just going to do this, this, and this. See, this was forgot about. So I'm glad I did that. We're going to go to Properties, Layer 4. And then we're going to get started. So net Q1 underscore 4. That goes to Q1 here. We're going to go ahead and rotate that around. Net Q1, that's going to go there. This is net Q2, so that's going to go here. And then we're going to go ahead and rotate that around. Or put it here. No, there's going to be, yeah, it can go here. And then this is net Q4. So it's going to go here, or relatively here. When we actually start routing it, we'll see what happens. And then this must be Q3. So that's all on the bottom. So my plan is to pop a via up right here and go directly in from this. So I probably need to back that up a little bit. But that is my plan, is to pop a via up at each of these and go directly in. So am I happy with my FET placement? Let's see. Am I happy with the way my FETs are? Current's it's going to be coming. It's going to come. It's going. And my center line is here. So let's move them up just ever so slightly. So grabbing the center. Where's my center? There we go. That looks pretty even between here and here. Let me go back, because that's going to be... No, that's a little too far. Let's go back down. Again, you can spend as much time as you want doing this kind of stuff. I spend too much time doing this kind of stuff, and it is okay. That's just barely above where I where I had it, isn't it? But I think I'm happy with that. I think I'm happy with that. That looks... Yeah, and then that'll... Yep, that looks fine. I'm happy with that. So I'm happy with that placement. Let's move capacitor over. So let's go ahead and route this then. We'll put this here, and we'll put this here, right? One more down. So let's go ahead and route this little section. So we're just taking, and then it is via, and then come right out of that. Right into that, just like that. Can I... So I'm going to fudge this a little bit. I'm going to reduce my grid to 100 millimeters and see if I can fudge it. I cannot fudge it. So rather than change my grid like that, I'm going to leave it on 250 and just be happy with it. So that one, and then just like that, and then always try to get my traces centered on the pad, but they don't have to be. See, that's just slightly off center. It's fine. It is perfectly fine. So these are all driven from the same signal. So we'll connect them together, and then we'll connect them together. And so now let's actually get to the driving part of the signal. So we will start with R15 first, which is just our discharge, our discharge resistor here. So we'll start with R15 first, and then we need R15 and R23. So here's R23, and R23 is just for pulling, well, really pulling down, to help pull down the FETs. So let's route this, and we're going to go just like that, and then R15 is going to go directly, just why is it not going down anymore? Just directly over here, and then we're going to adjust that, and then adjust this, so it looks okay. And then R15 goes to C10 right here, so I'm just going to put it as near to these as possible. So I want to put it over here as near to these as possible. Excuse me, I want to put it over here as close as possible. I'm going to put it over here as close as possible, and then that was an odd glitch. And then I'm going to do this with a via, because this will be where the copper pour is. So there's our discharge line ran. Now let's run the charge line. So let's get started with the charge line. This section here is, I believe, the original section coming out when it was on the top side. And so I'm going to change these around just like that. And then I need, so this is backwards then. So I need R16 to be over here. And then I need this to be the same. Oh. This to be the same. Just like that. Just like that. And then let's take and move it all, because I have nothing more to route off of the chipset except for the thermistor part, and I have a 4-layer board now, so I haven't got to worry as much about all of that. So let's do that. We can do that coming directly out. And then just like that. And then we're going to go into our other circuit here, our other drive circuit. So I want that to be, do I want to be close here, or do I want it to be close out here? I think since this is my ESD protection here, I think I want it to be as close out here as I can get it, because it is my protection. So let's do this. We'll put it right here next to the drive line. Actually, we'll put it before the drive line. So physical placement is important. So if I have some kind of TVS or something that I'm trying to fight, in this case, we don't want the charge line to go above we don't want it to go above a certain threshold. So we don't want to go 16 volts above whatever power ground is in case there is a surge or something. You want to put it before your gates. So even though I could put it way down here, then whatever the ESD event or whatever the spike event is going to travel across these two gates before it gets to my TVS. So you want to put it before your signal gets to whatever. That is something that I see a lot of designers miss for some reason. I'm still not sure why, but it's kind of common sense a little bit. You want to put it where your signal comes in. Anyway, not a pet peeve or nothing, but so we're going to do this. We're going to route this, and then we're going to put we want to put it on the TVS. We're going to put our power ground here, and of course this will be power ground when we're finished with it. And then we're going to go just simply down like this, and bam, right into there. So we have a very, very few nets to finish. So we're going to run this power ground sense trace, and we're going to just run it up here, and then we're going to put a via here. There we go. We're just going to put that is the load removal. Pin number 14 is load removal. So it knows whether the load has gone off the system or not, and so this is a sense line. We want the resistor to be as close as possible to the chipset. So let's see what other nets we still have to route. We still have to route our thermistors, and we still have to route our system present. So let's go ahead and take care of our system present first. Now R11 right here, and then over, and then right there, and then we're going to put a via, and then simple right there. This is just a dirt simple board. And then for our thermistor, we're going to put a via right here, and then we're going to go ahead and route that on layer. Oh, I do not have my view configuration up here, so there we go. We need a layer 2 and layer 3, and we're going to go ahead and route that on layer 3. I'm going to put, so it's going to be technically signal, and then ground plane, signal plus ground, and then power. The reason for that is I want there to be a return path in between every signal. So if I've got 2 signal layers that I need to run, but the top has got to be powered. BMSs are a little different than other high-speed designs because you have to have sort of a dedicated power layer, sometimes a dedicated power and signal layer, so you can't do a normal stack up. So what I like to do is the bottom layer will be signal, top layer will be power. Then the layer 3 will be my ground plane. And then my layer 2 will be another signal plus ground. So that way any signals ran on layer 2 have layer 3 as their return path. Any signals ran on layer 4 has layer 3 as their return path. So I'm sort of treating layer 1 as a separate layer from the rest of them, even though it does have some signals that need to return. I really make it a 3-layer board, if that makes any sense to anybody listening out there. I really kind of make it a 3-layer board and ignore the 4th layer. Is it right? Is it not right? I honestly do not know. I don't know if it's correct. I don't know if it's not correct to think of it that way, but that's just how it makes sense in my mind, so that is how I do it. So I'm going to take thermistor 1, we're going to bring it out, and then we're going to go on layer 3 and we're just going to bring it up. Oh, I'm sorry, I did that wrong. That should be layer 2. So I'm going to bring it across layer 2. Layer 3 is going to be a ground plane when I'm done with it. Layer 2. Now, should I have already made a plane and done all that stuff? Maybe, but I don't do that until last, just so it's not in the graphics. And then, while I could turn it off and all that stuff, I just don't like to do that. People have different ways of how they do things. I like to see everything at one time. I don't turn off my net labels. my rat's nest. I don't turn it off. Some people, that annoys the snot out of them if they have a rat's nest. I don't turn it off. And I have no other comment for that. I don't know what else to say. I just don't. I just like to see everything at one time. That's not, some people's preference, but I just like to see everything at one time. So there we go. There's that. Layer 1 for thermistor 2. Now, this thermistor is for the charger. The charger has to see a thermistor. So we have to have a onboard thermistor for the charger to read. Now, I thought about spoofing it, just putting a 10K resistor and then letting the BMS handle it, but why not put 2 on there if you can do 2? So the reason I'm not doing a surface mount thermistor is because it's a lithium-ion pack. You really need the thermistor sitting against the cell stack. That's why we're doing the 4-pin connector, because there will be a 103 or 2 103 ATs coming out of that, and then taping to the cell stack. So I think that is all of our nets routed as far as that goes. What are you? Oh, I've forgotten about a resistor. What is R26? Where do you? Oh, you are the system present resistor. Okay. You are the extra system present resistor. That's what you are. So we're going to go, we're going to put you on layer 4. We're also going to do your designator. And then we're going to go 0.8 and 0.2. And then I'm just going to put you right here. I'm just going to put you right here. Happy little resistor. Just right there. That's it. And so I'll do this and this, and then I'll do this. And I'm just going to put a via out here, because this is where the pack plus plane will be. And then, of course, my output capacitors here. So I'll just kind of even them up a little bit. Just kind of eyeball it. And there we go. I think that is everything routed other than our copper pores. So let's start on our copper pores. I'm going to exit our split screen here. And then we'll do our copper pores. So layer 1, and then that will be where all of our copper is on layer 1. So before, with the design, the way it was. So with the design the way it was, if it'll focus, you see how little copper there is on there? Just how little copper. And I want this thing to be able to carry 23 amps continuous. And my initial thought was, I'm only going to use the tool for a few seconds. These traces can handle 23 amps for a few seconds. It's fine if I got to drill a hole or I've got to cut a piece of wood. But then I got to thinking, that's just taking shortcuts. Why would I do that? Especially when 4-layer boards aren't expensive anymore. They really aren't, unless you're buying millions or hundreds of thousands of PCBs. When you're like us, or when you're like me and you buy a couple hundred, maybe a couple of thousand, a 4-layer board versus a 2-layer board really is not that. You're not going to save that much money. So I decided to do it right. So let's do our copper pores, and then we'll make, and then we'll do our ground planes for layer 2, layer 3, and then, and then we'll be finished. And the reason for that is because of our ground. So there's not enough room on here to put enough copper on the top and then have a good ground plane for your chipset. So that's really the reason. This is definitely overkill. Definitely overkill. But why not be overkill? So I'm going to change my grid to 500. And then we're going to go up. And then I always just go outside. Then we're going to go down. Down. And then we're going to go back. Oh. Across. And I'm just going to make this one solid plane here. Just like this, and then this will be net battery ground _1. So I'm going to put this back the way it needs to be so I can finally read it. Net battery ground _1, and that is too big. I apologize. I should have done it. like that. There we go. And so this copper plane is large enough to carry the current that we need. That is large enough there to carry all the current that we need. That is large enough. Actually, I'm going to make it a slightly bigger. Let's get it that close to our the middle. I'm not happy with the way that looks. Let's redraw that. Instead of doing that, let's start here, and then we're going to go, I'm going to put some curves in it just so it looks a little nicer. Does not add any kind of electrical property, but it'll look a little better. Just like that. But wrong one, battleground _1, and there we go. That's a whole lot better. I like that a whole lot better. Just has them little chamfers on it. Just makes it look a little bit more aesthetically pleasing. Not hugely. So there is that. And then we've only got 3 vias here in this. It's not going to make that much difference, and that is plenty of copper room to carry all of that current. And then same thing here. We're going to start here, and then let's go up. We'll go across. Then, if you hit backspace, it takes you back one. So we'll go across, and then down, and then up. Like this, and then down. And then like this, and then or like this, and then over. And we can make adjustments. I don't know how many of you have ever seen Bob Ross. It's your PCB. You can make it like you want. Bring this over, and then this up. Yeah, like that. Like that. Okay. And then for this, I don't like how close it is to that. So let's back it up, and then we'll pull it up like that. And then this is net C10_2. I probably should have labeled it, but hey, it's okay. And then we only have the 1 via in it. So again, that should be plenty of copper area, especially with a 2-ounce PCB. I'm going to do this in 2-ounce copper because, again, this is as nice as I can make it. So that should be plenty of area to carry current. And then I'm going to, so you see this, I need to pick a place in between this. So I'm going to change my grid to 250 so I can pick this spot, and then this spot, and then this spot, and then this spot like this. Because these are so close together, the copper area hasn't got to be as much. And so this is Q1_5. So I'm not going to assign that just yet, because for the FETs, I like to put vias in them and then put a small copper pore on the bottom just to help with the heat. So that's what I'm going to do. Well, no, I don't really need to do that. I don't, yeah, I'm going to go ahead and do it. I have all this room to do this in. I'm going to do that. So what I'm going to do is I'm going to reroute this down and then back up to get it out of the way. And then I'm going to make this area here on all the planes a copper pores, just for heat. So yes, I am going to cut into my ground plane. Oh no, it's going to be so terrible. It will be fine. So let's do that, and then we'll do this, and then we'll go ahead and take this back to no net so I can see where I'm putting my vias. Then we're going to do, also, Altium has started doing this where if you put a via into something, it glows green. Well, that's kind of annoying when you're doing something like this, because I I can't see where I'm putting my, and it didn't used to do this, and I don't know if an update changed the rules somewhere and I didn't know or I missed it, but my Altium did not used to do this. It is quite annoying. For as much money as this cost, I don't like it doing that. So I'm going to do vias, Control C here, and then Control V, and then Control V. And so there we go. Then I've got my copper pour here, and I'll go ahead and put the net back Q1_5 the where it needs to be. And then I'm going to take and copy it. So Control C, copy it here, and then layer 2, we're going to edit, paste special, paste on current label, and keep net name, paste here, paste special, layer 3, and then paste special, layer 4, just like that. It's just something that I like to do. Is it necessary in this design? No, it's not necessary at all. Do it anyway, but it's not necessary. So, and then we go to our power ground plane here. So let's go ahead. We'll start here so it looks even, and we'll start here, and then we'll start here. We'll come across, then it's a little too steep of an angle. There we go. And then we'll bring it right in here. And then this will be power ground. Just like that. That will be power ground. And so that should be plenty of copper to carry everything that we need to carry. I'll go ahead and route these two while I'm here. Change the trace width. I'll route those two while I'm here. Oh, these are backwards. Okay. I was wondering why that was showing that way, and it's because they're backwards. So I'll go ahead and change these two as well. And then we'll go ahead and route these to power ground, to themselves, and then it'll be to that copper pour when we're finished with it. So now to our other copper pour. Let's move the fuse. Change our grid back to 500. Let's move our fuse back a little bit. There we go. Then we'll go from, where are we at? 1, 2, 3, 4 dots. So 1, 2, 3, 4 on the 5th dot. We'll go over, and then we'll do a slight curve to here, and then a slight curve back to here, and then here, and then here. Now, all of this copper back here is not really doing anything. It's not really helping anything, but it just makes it look even. That's all it is just makes it look even. And the reason I'm doing my copper pours way out here is because I have the board outline rule set up to where it'll automatically cut it off. So there is that going in there. Does it look okay? It looks okay. I'm not a big fan of this. Is there something we can do there? I think it'll be fine. Not a big fan of that. I'll think about it, but let's go ahead and route the rest of this while we're at it, and then I'll think about that. So we want to do this, and we want to kind of match that angle there. We'll come across, down, and then messed that up, didn't I? Okay, so let's adjust this because it's in that Pack Plus. So we'll go ahead and adjust that down. I think I need to move C5. I think that's going to look stupid. Let me see. Oh yeah, that looks. What is this copper doing out here? That looks stupid. So let's do this again. Instead, let's go like this. Again, looks are half the battle. Looks are half the battle. So, you know, when you're worried about stuff, you worry about looks. You worry about how it looks. Something bad happens, you worry about how it looks to people, how it looks with this or how it looks with that, or those kind of things. Looks are really half the battle. So I'm going to move these two components over here. I'm going to move them over here because I can put them here. That's what I'm going to do. I'm going to put them here. And then I'm going to make this copper port just a little bigger. Not much, but just a little bigger. And pack plus like that. Yeah, see, now that looks okay. That looks okay. Let me, again, I have no plan, so I'm just kind of winging this. Let me pull it up as far as that one goes and then shorten this up. Yeah, that looks a lot better. I'm a lot more happy with that. Yeah, that looks a whole lot better. So, yep, that looks a whole lot better. Although I'm not a fan of this now. Now I'm a fan of it. Okay. Nope, there's still one more thing we're going to need to correct. So I want to match this chamfer here in this copper pour because I've got OCD. So I'm going to put a polypore cutout and I'm going to trace it. I'm going to trace it here. Right, and then I'm going to move it and I want to flip it and I'm going to put it here. Yeah, there we go. Slightly off. There we go. And look at that. There is that's a little cheat for you. Instead of having to redo the whole copper pour, you can just place a polypore cutout, trace it for whatever the shape you want, and do it again. So yeah, I'm happy with that. That looks very good. I'm very happy with that. I think it will look very cool as a PCB. It's very even. I like it a whole lot. Let me just do a few more little changes. I think this will look better as an even copper plane. Like that. Yeah, that will look better as an even copper plane. And then, yeah, I'm happy with that. I'm perfectly happy with that, except for this. We're going to do something different right here. So let me do this and this. I can get rid of these two. The length of these don't matter a whole big bunch. So let me move the thermistors up here in the open space. Move that one up above. And then to layer 2, we're going to like that. Let's make it even. Oh. There we go. And so that got rid of 2 of them. And then this is just the ground reference for the thermistor. So, well, I'm an idiot, and I just realized a huge mistake. So, I just realized a huge mistake. So, the thermistor for the charger needs to be tied to power ground, not to battery ground. And the reason for that is so that way, in case the fetch trip, it can still read the thermistor, because if the fetch were tripping, you can no longer read the thermistor. So that is my bad. I just never thought about it. So yeah, thermistor 2 needs to be tied to power ground, not to battery minus, so that way whatever's out here can still read the thermistor. So that was a mistake on the last design. I forgot, and I got to looking at the connector, and I said, that's not right. And now I know why it's not right. So let's update this design. We'll save that. I need to expand that back out too. Let's expand that on back out. Expand this on back out to where it's correct. And then we'll save that. We'll go ahead and... Oh, I haven't saved the PCB design. That would have been bad if I lost that. And then we'll update it. And don't add the room. Execute changes. And now this is going to power ground. So this is not an ideal situation here. Having to run this all the way to there must hold on just a second. There must be a track stuck in this. So I'm going to do this. We should be able to highlight it and delete it. There. This is not the ideal situation, having to run this all the way back to power ground, but I still want it to be that way. So what I'm going to do is I'm going to put a via. I'm going to take and I'm going to put a via. No, I don't like that. So again, I'm just winging it. So we're going to back this up, so I can back this up, and I can pull this up so it looks good. And I'm going to back this up. I'm going to back this over, and then I'm going to do this so that way I can do this and do this and this. And I'm going to put a via here, and then I'm going to run a track to power ground. That is not ideal. But that's what happens when you work with a charger, or we're going to make a charger that does not have, that cannot work with a discrete thermistor. So we're just going to run this all the way back to power ground and put a via. Again, not ideal, but but the way it's got to be. So now we only have one via here. And now the charger can read the thermistor out of the battery pack. Can't believe I missed that. I can't believe I forgot about that. But yeah, that is a thing. So I guess it's a trap for everybody, even experienced people. So if you need to make sure you're thinking about that when it comes to thermistors. Okay, so let's get everything finished up. I'm going to do these capacitors here, and even though they're not centered, they are centered in between the copper pour. So let's put them over here so they look like they belong. Are the capacitors really going to help? I really don't think so. They're not large enough, but it's just the way design is. In a thing this large, I don't think it's really going to help that much. But it's just the way the designs are, so I just do it just because I can. And so that should be the last of our nets routed. Oh, we need to route Pack Plus here. There we go. And so that should be the last of our nets routed except for our ground plane. So layer 2 is we're just going to do a copper pour over the whole thing. Now, some people may argue that it increases your RF susceptibility if you do a copper pour over the whole thing. And there is some merit to that argument. I'm not arguing that. There is some merit to that argument. However, in this configuration, it's not really that big of a deal. Also, I'm going to copy it, or I'm going to put it to ground, battery minus, and then I'm going to copy it. But I don't really. I don't. This isn't a high-speed design. I don't really subscribe to that. But it's okay. Now, this should be a... I really should make this a plane. except I don't remember how to do it here, and I'm recording. And so I'm just going to make it a copper pour. It will be fine. The Gerber files don't care. So, at least in this design, the Gerber files do not care. So I'm just going to do a copper pour here on this layer. I apologize. I do not remember. I do not remember how to do it offhand, just in the recording. That is my bad. And then here on the bottom layer, I'm going to do some manual copper routing here. So first of all, I'm going to take and put some vias up here in the corner. Oh. Sorry, I do not need to put vias. I forgot. The battery minus comes from the connection here. That's to avoid it being influenced by high currents. So I'm going to take and I'm going to just put my bat minus. See, my main. I don't like that either because my main battery ground is here. So let me do this. I'm going to do a thicker trace here, and I'm going to put it behind. Let me think about this for a minute. All right, so I think what I'm going to do is I'm going to put a copper pour, a small copper pour here. So we're going to do this, and then we're going to go up over here and then back down like this. And then this will be bat minus. And then we're going to put our vias to connect to back minus up here. And then that will keep everything away from the main current path. That will be here. And then we'll go ahead and connect our back minus back to this. And then yeah, I think that'll be fine right there. Okay, so the last thing to address is our bottom layer. As you can see, our bottom layer has no copper. Has no copper at all. And I do not want to put a bunch of ground plane on the bottom, because I don't want to via stitch it and then have that cut into our top copper pour. So what I'm going to do is I'm going to just duplicate our top copper pours in order to get the copper even, so that way the manufacturer will not yell at me. Is it unconventional? Yes. And the reason I need to do that is because I don't need to cut into my top power plane. So I want these top power planes to be as solid as possible. This is why BMS design is a little different than everything else. Everything else you've been taught, you don't sacrifice the power in a BMS design. In everything else, signal integrity, you can route the power funky any way you want to. Everything's below an amp or right at an amp. It's not really high power and all those kind of things. Or if it is high power, you put in a dedicated power plane. BMS design isn't like that. So I don't want to sacrifice the top copper. So I'm just going to duplicate the top copper and then just put in some vias to tie it together. That's all I'm going to do. Is put in some top copper, put in the top copper on the bottom plane with some vias to tie it all together. That's all I'm going to do. It serves no electrical function. Oh, I did that wrong. Edit, paste special. Serves no electrical function. Just is to sit here as empty copper, basically. Okay, so one of the last things I'm going to do is I'm going to change my via style. I'm going to do 1.2 diameter and a 0.6 hole, and I'm just going to put some bigger vias around the edge of these copper pours just to tie them in a little bit better. Not completely necessary, but I do anyway sometimes. Well, there are all the vias finished, and I did untint them because it looks cooler with them untinted. That just makes the PCB look more than it is if you just have some untinted vias. But there we go, tying all those extra copper pores together just so the manufacturer will be happy. And then we'll move our model number down here just in the middle, and of course change it to number 2 because this is revision 2. And then the last thing to do is to do our design rule check. So we need to go to design or tools, design rule check, and run design rule check. So run design rule check. We have a few things that are wrong. Let's see here. Do we have any net antennas? That's what I was afraid of. Net antenna. Let's take care of that first. Okay. That's just a simple fix right there. And then what is next? We have a silk to solder mask clearance, which is here. Oh, we have to fix the solder mask. Okay, so let me take a minute to fix all the solder mask stuff, and then we'll go back to our design rule check. Okay, and there we go. There are all of our designators fixed. Well, not this one. That is our last designator, I believe, that needs to be fixed just from looking at it. If I missed one, I'm sure you'll let me know in the comments. But there we go. There is that. All of our components and all of our designators are nice and fixed. Okay, now on to the rest of our design rules check. So looking at our design rules check here, the silk to solder mask clearance, I believe we got that. And then the board out edge clearance. What is that between J3? Oh. What? Okay, so let's just take components and just move J3 back. Oh, no, not that much. And just bump it back. Just a little bit. And see. All right, so let's do design, tools, design rule check, run design rule check. Now we've got 2 more errors from fixing the thing. So let's see that. I need to take my sensor bar off. So that bar you see at the top, the design rules check shows your file directory where the design rules check is held, and so I have to put that bar up there so that way you can't see things you're not supposed to see. It's a sensor bar. That's what it's for. It's to censor things. So let me throw my sensor bar back up here, and then we'll run our design rules check one more time and make sure that everything is good. Yep, we have 0 errors, as you can see. So there we go. Remove the sensor bar, and there we go. Our PCB is ready to go, and I have to admit I'm quite happy with it. It can carry all the current that I have designed it for. This can carry 23 amps continuous, no problem. With 2-ounce copper, it can probably carry 30 amps, no problem. The output's a lot nicer, and then the layout on the bottom is a lot nicer. It's just a lot nicer PCB. Now, is this overkill? Of course it is. But I wasn't happy with it, so I decided to rather go overkill than just to let it be. So, is it overkill, and there's a few parts of it that are weird because there's not enough components, like all of this copper on the bottom, all of this copper that's just floating. Well, it's not floating, it is tied to a net, but it's just kind of there just to fill in the dead space because this is the only components that we have. But I wanted room to run all of this copper, and there's not enough room in this, 1/4 of an inch I have here to put all those components in. So I hope you enjoyed watching today's video. I am now happy with this. I'm going to save it. I'm going to order it, and then we will put it together when it comes in. But I'm happy with this. I'm happy I took the time to do this. If you enjoyed today's video, please like, share, and subscribe. And I will see everyone in the next video.